Before we start talking about our project, we first need to understand where we're coming from. And where we're coming from is from improving Roche's current design. Roche employs the Benchmark Ultra Plus to stain up to 30 patient slides at a time. This device operates using high pressure to drive up to 7 different reagents onto the patient slides with the use of 3 different nozzle heads. The problem with this high pressure system is the need for many valves and the waste from non-precise dispensing. This project, named Bench 2.0, is a benchtop testing system that investigates the Phoenix pump, which operates without valves and without pressure. Its purpose is to define the pump boundaries under Roche's device workflow conditions. Roche will inherit Bench 2.0 in order to further test and validate if integrating the Phoenix pump as the dispensing mechanism for their device is cost-efficient and environmentally friendly. The benefits of replacing the pressure-driven dispensing system with a valveless pump would be the reduced risk, maintenance cost, and reagent waste. This provides the device with a greater sense of simplicity and increased sustainability. This directly correlates with increased patient outreach through increased reagent volume supplies to hospitals.
Hi, my name is Danielle. I'm a biomedical engineer and I'm the procurement lead.
Hello, my name is Gabriel. I'm a biomedical engineer and I'm the team lead for this project.
Hi, I'm Enoch Du and I'm an electrical engineer.
Hi, I'm Nico Martel and I'm the software engineer for this project.
Hi, my name is Daniel Molest and I am a mechanical engineer.
My name is Luis and I'm the systems engineer of this project.
Hi, my name is Marie and I'm a mechanical engineer on the project. The Bench 2.0 supplied its fluid through an open or pressurized container, where it will go through the Phoenix pump by the synchronous rotation and reciprocation of the ceramic piston in the precisely mated ceramic cylinder liner. Now, the ceramic piston is controlled by the rotary motor, and when it moves, it'll accurately pump fluid in one direction without allowing any backflow through the pump. The fluid will eventually reach the fiber optic sensor at the end of the tubing line before the nozzle, which indicates to the user that the entire tubing line has been primed, which means that every single cycle after this step will dispense fluid onto the slide without introducing bubbles into the tubing. This means that every single rotation of the rotary motor after this point will dispense fluid onto the slide. There are 3 basic steps to the Bench 2.0 system workflow. The first utilizes a dual rinse nozzle, which adds the main bulk of reagent onto the slide. The second step utilizes the volume adjust nozzle, which adds precise amounts of fluid onto the slide to precisely adjust the amount that the user desires. The third utilizes the jet drain nozzle, which blasts a jet of water over the slide, which removes the reagents by draining them off.
So we started off our project with the Phoenix pump provided to us by Roche. Initially, we wanted to work on characterizing the pump and the fluid flow it can provide through our 3 different nozzles: the dual rinse, the volume adjust, and the jet drain. So in characterizing this pump, we realized that there were some limitations, and that was due to the controller we were using. So we talked to the Roche team and our sponsors at FMI, and we discovered that there was a different controller better suited to our needs, the triple axis trinamic controller. When we switched to that about halfway through our project, we found a lot better results in the flow rates through our different nozzles. After switching, we shifted focus to making this benchtop system as user-friendly as possible for our Roche sponsors. That included building out this mechanical frame, software integration with our sensor for priming, and overall user-friendliness.
So taking a deeper dive into our Bench 2.0 system, we're going to go ahead and start here with our water tank. It will have fluid that will be pumped from our Phoenix pump that will go through our tubing. Now, our Phoenix pump will contain two motors, specifically the linear and rotary motor, that will be connected to our triple axis dynamic controller that contains 2 outputs for both those linear motors and rotary motors. Now, the Phoenix pump is going to have one singular piston that will allow the fluid to pump through our rotary motor, that will exit out through this tubing here, that will exit, then once it reaches to our nozzle head, it will be able to our nozzle head will allow it to dispense onto our slide, and our slide will be onto a slide holder, and our weight scale will allow it to take any measurements from the fluid that was dispensed. Some other components that we do have is going to be our sensor. Now our sensor will be connected to our tubing. This will be powered from our Raspberry Pi, which as you can see here. Now this sensor will give feedback to our user whether or not there is liquid present in our fluid to allow for us to run the entire system.
So going over the software real quick, on the user's computer, we have the UI running. You can see that on the left side, we have the control center, which houses all of the controls for the system. We have the speed, the strokes, the acceleration, the flow direction, and then for end case settings, we have the duration and the iterations. We also have a visualizer for the data collected during any run. We have the weight monitor, and then we have the tear scale button that allows the user to tear the scale. And then we have the execute button for the command set that the user puts in. So for our next demonstration, we will show how the set of commands works. So we'll start with a stroke amount of 20 at a speed of 500. Then for the second one, we will use a stroke amount of 10 for a speed of 100. Now we will tear the scale before starting our next execution, and then clicking execute. As you can see, it ran twice. It ran the command set that we had set appropriately. It first did its stroke amount of 20 at 500 speed, and then it ran slower at a speed of 100 for 10 rotations. The final demonstration that I'll show is how we can export our data. So you can see that our data is aggregated on the right. We can then go into our file menu, click export data. It will then show your file environment based on where you started running the program. Then you can choose a file name for it. We'll call this one example. We'll then save our data. And now we can go into our files and look at the CSV. And as you can see, it has our latest set of data shown in that CSV file. We can also export our command sets. So we can go to save config. We'll call this one test 1. It's saved to where you decided to save it. And now looking at that, we can see our two examples of our command sets. We both have the first set, which is the speed of 500 with the stroke count of 20. And then we have the second one, which is the speed of 100 and the stroke amount of 10.